Vitruvian geometry. Living organisms, the bodies of animals and human beings are built upon the principles of symmetrical motion. In order to understand these principles, we need to examine a simple schematic example of symmetrical motion. Imagine a cube, composed of 27 small cubes, and then imagine that cube expanding and contracting. During the process of expansion, all the 26 cubes lying around the central cube will retreat from it, and on contraction will approach it again. For the sake of convenience in reasoning, and in order to increase the likeness of the cube to a body containing molecules, assume too that the cubes have no dimension, that they are nothing but points. In other words, take only the centers of the 27 cubes and imagine them connected by lines both with the center and with each other. Visualizing the expansion of this cube, composed of 27 cubes, we may say that in order to avoid colliding with another cube and hindering its motion, each of these cubes must move away from the center, that is to say, along the line which connects its center with the center of the central cube. This is the first rule. In the course of expansion and contraction, molecules move along the lines that connect them with the center. Further, we see in our cube that the lines connecting the 26 points with the center are not all equal. The lines drawn to the center from the centers of the corner cubes are longer than the lines drawn to the center from the centers of the cubes lying in the middle of the sides of the larger cube. If we suppose that the intermolecular space is doubled by expansion, then all the lines connecting the 26 points with the center are at the same time doubled in length, but the lines are not equal. Therefore, molecules move with unequal speed, some of them faster and some slower. Those further removed from the center move faster, those lying nearer the center move slower. From this we may deduce a second rule. The speed of the motion of molecules in the expansion and contraction of a body is proportional to the length of the lines which connect these molecules with the center. Observing the expansion of the big cube, we see that the distances between all the 27 cubes are increased proportionally to their former distances. If we designate by the letter A, lines connecting the 26 points with the center, and by the letter B, lines connecting the 26 points with one another. Then, having constructed several triangles inside the expanding and contracting cube, we shall see that lines B are lengthened proportionally to the lengthening of lines A. From this we can deduce a third rule. In the process of expansion, the distance between molecules increases proportionately to the increase of their distance from the center. This means therefore that the points that were at an equal distance from the center will remain at an equal distance from it, and 2 points that were at an equal distance from a third point will remain at an equal distance from it. Furthermore, if we look upon this motion not from the center, but from any one of the points, it will appear to us that this point is the center from which the expansion proceeds. That is to say, it will appear that all the other points retreat from or approach this point, preserving their former relation to it and to each other, while this point itself remains stationary. In other words, the center is everywhere. The laws of symmetry in the structure of living organisms are based on this last rule. But living organisms are not built by expansion alone. The element of movement in time enters into it. In the course of growth, each molecule traces a curve resulting from the combination of two movements, movement in space and movement in time. Growth proceeds in the same direction, along the same lines, as expansion. Therefore the laws of growth must be analogous to the laws of expansion. The conditions of expansion, that is, the third rule, ensure the most rigorous symmetry in freely expanding bodies, because if points that were originally at an equal distance from the center continue always to remain at an equal distance from it, then the body will grow symmetrically. In the figure produced by an ink blot on a sheet of paper folded in two, the symmetry of all the points is obtained because the points on one side come into contact with the points on the other side. To each point on one side there corresponds a point on the other side, and when the paper is folded these points touch one another. From the third rule above formulated, it must follow that between the opposite points of a four-dimensional body there exists some relation, some affinity which we have not hitherto noticed. To each point there corresponds as it were one or several others, linked with it in some way unintelligible to us. That is to say, this point is unable to move independently. Its movement is connected with the movement of other corresponding points that occupy positions analogous to its own in the expanding and contracting body. These points are precisely the points opposite to it. It is, as it were, linked with them, linked in the fourth dimension. An expanding body appears to be folded in different ways, and this establishes a certain strange connection between its opposite points. Let's now try to examine the way in which the expansion of the simplest figure is effected. We will take this figure not in space even but on a plane. We will take a square. Then connect the 4 points at its angles with the center. We connect with the center points lying in the middle of the sides, and finally points lying halfway between them. The first 4 points, that is, those lying at the angles, we will call points A. The 4 points lying in the middle of the sides of the square we will call points B, and the points lying also on the sides of the square between A and B, there will be 8 of them, we will call points C. The points A, the points B, and the points C lie at different distances from the center, and therefore on expansion they must move with unequal speed, all the time preserving their relation to the center. At the same time, all the points A are connected among themselves, just as the points B are connected among themselves and as the points C are connected among themselves. Between the points of each group there is a strange inner connection. They must remain at equal distances from the center. Let's now suppose that the square is expanding, or in other words that all the points A, B, and C retreat from the center along radii. As long as the expansion of the figure proceeds unhindered, the movement of the points will follow the above-mentioned rules, and the figure will remain a square and preserve a most exact symmetry. But let's suppose that suddenly some obstacle has arisen on the path of the motion of one of the points C, forcing this to stop. In such a case there are 2 possible alternatives. Either all the other points C will continue to move as if nothing had happened, or they too will stop. If they continue to move, the symmetry of the figure will be broken. If they stop, it will mean a strict observance of the deduction from Rule 3, according to which points at an equal distance from the center must on expansion remain at an equal distance from it. In fact, if all the points C, obeying the mysterious affinity which exists between them and the point C which met with an obstacle stop, while points A and B continue to move, then the square will be transformed into a regular, perfectly symmetrical star. It is quite possible that a similar thing happens in the process of the growth of plants and living organisms. Let's take a more complicated figure, in which the center from which the expansion starts is not a point, but a line, and in which the points retreating from the center on expansion are disposed on both sides of that line. An analogous expansion will then produce not a star, but something resembling a dentate leaf. If we take this figure as lying in 3-dimensional space instead of on a plane, and suppose that the centers from which the expansion develops lie on not one but several axes, we shall obtain on expansion a figure that may resemble a living body with symmetrical limbs, etc. If we then suppose a movement of the atoms of this figure in time, then we shall obtain the growth of that living body. Laws of growth, that is, of motion originating in the center and proceeding along radii in expansion and contraction, establish a theory which may explain the causes of the symmetrical structure of living bodies. The definition of states of matter in physics became more and more conditional over time. At one stage there was an attempt to add to the 3 generally known states, solid, liquid and gaseous, a 4th, radiant matter, as the greatly rarefied gases in Crookes tubes were called. Then there exists a theory that considers the colloidal, gelatinous state of matter as an independent state of matter, different from solid, liquid, and gaseous. Organized matter, from the point of view of this theory, is a kind of colloidal matter, or is formed from colloidal matter. The concept of matter in these states was opposed to the concept of energy. Then appeared electronic theory, in which the concept of matter became little different from the concept of energy. Later came various theories of the structure of the atom, that introduced new ideas into concepts of matter. In this domain more than any other scientific theories differ from ordinary life concepts. For a direct orientation in the world of phenomena it is necessary for us to distinguish matter from energy, and it is necessary to distinguish the 3 states of matter, namely solid, liquid and gaseous. At the same time, it must be recognized that even these three states of matter known to us are distinguished clearly and indisputably only in their classical forms, like a piece of iron, the water in a river, or the air that we breathe. However, the transitional forms overlap and are not clear. Therefore, very often we do not know exactly when one state passes into the other, cannot draw a definite line of demarcation between the various states of matter, cannot say when a solid has been transformed into a liquid, when a liquid has been transformed into a gas. We presume that different states of matter depend upon a different cohesion of molecules, on the speed and properties of molecular motion, but we distinguish these states only by their external traits, which are inconsistent and often become commingled. It can be said definitely that the finer the state of matter, the more energetic it is considered to be. That is to say, containing as it were less substance and more motion. If matter is opposed to time, then it will be possible to say that each finer state contains more time and less matter than a coarser state. There is more time in a liquid than in a solid. There is more time in gas than in liquid. If we accept the possibility of the existence of still finer states of matter, or rarefied matter, then they should be more energetic than those recognized by physics. They should contain, according to the above, more time and less space, still more motion and less substance. The logical necessity of energetic states of matter has long been accepted in physics and proven through very clear reasoning. We could never determine what matter and force really were, but always considered them opposite to one another, that is to say, we could define matter only as something opposite to force and force as something opposite to matter. However, the old views of matter as something solid and opposite to energy have considerably changed. A physical atom formerly regarded as indivisible is now recognized to be complex, composed of electrons and quasars. Electrons and quasars are, however, not material particles in the usual meaning of the word. They are better defined as moments of manifestation of energy, moments of elements or force. To put it in a different way, whilst representing the smallest division of matter possible, they are at the same time the smallest divisions of force. Electrons can be positive or negative. It is possible to think that the difference between matter and force consists simply in different combinations of positive and negative electrons. In one combination they produce on us the impression of matter, in another combination the impression of force. From this point of view, the difference between matter and force, which constitutes so far the basis of our view of nature, does not exist. Matter and force are but one and the same thing, or rather, different manifestations of one and the same thing. In either case, there is no essential difference between matter and force, whether one must pass into the other. From this point of view, matter is nothing but condensed energy. If this is so, then it is quite natural that degrees of condensation might be different. Fine rarefied states of matter must therefore occupy a middle position between matter and force. In his book, Unknown Forces of Nature, C. Flammarion wrote, "Matter is not at all what it appears to our senses, to touch or vision. It represents one single whole with energy, and is the manifestation of motion of invisible and imponderable elements. The universe has a dynamic character." Guillaume de Fontenay gives the following explanation of dynamic theory. In his opinion, matter is in no way the inert substance it is often considered to be. Take a spoked wheel and place it horizontally on an axle. Whilst the wheel is not moving, take a rubber ball and make it fall between the spokes. Now make the wheel turn slowly. The ball will fairly often hit the spokes and rebound. If we increase the rotation of the wheel, the ball will not pass through it at all. The wheel will become for it a kind of impenetrable disc. A bicycle wheel would serve the purpose even better, as its spokes are thin. When the wheel is stationary, a rod will pass through it 9 times out of 10. When in motion, the wheel will repel the rod more and more often. When the speed of its motion is increased, it will become impenetrable, and all efforts at piercing it with the rod will strike as against steel armor. Reference: Camille Flammarion, Les Forces Naturelles Inconnues. Published in Paris 1927, edited by E. Flammarion, see page 568.